today I will solve IMO 2023 problem 1. I think this was the easiest problem in the IMO history. In this problem we need to find all composite integers greater than 1 such that if we write down all of its divisors, d1, d2 up to dk, then di must be a divisor of di plus 1 plus di plus 2. When we see the problem, we can easily see that the answers will be only n equals to the prime number into any power k. It's easy to verify that all numbers works, like because the first one is 1, the second one is p, next one is p square, and so on, and last one would be p to the k must be p to the k. So we can see that p to the I always divides p to the I plus 1 plus p to the I plus 2. Clearly, all numbers who has only one prime divisor works for our problem. And now discuss the case if our number n has at least two different prime divisors, like n equals p to the alpha 1 times q to the sum in number power of p1. If we look at, now we need to look at from the backwards, like n equals this number, and let's assume that p is less than q. This is n. What can we say about the dk minus 1? dk minus 1 would be p to the alpha 1 minus 1 times q to the beta 1. And now we can continue this process until we get the number. Q will be decreased only. So at some point we get the number who will be like p to the alpha 1 times q to the beta 1 minus 1. And in this case, what can we say about this number? Like all numbers between them will be multiple of p, or like if we take this p to the k and p to the m times q to the beta 1. All numbers will be multiple of p to the m at least. And what can we say about the last two numbers between before the p1 times q to the beta 1 minus 1? This number must divide pm to the q to the beta 1 plus pm plus 1 to the q to the beta 1. But what can we say about these numbers is that alpha is clearly more than m, and alpha is clearly more or equal to m plus 1. And if we see that left hand side, this number is divisible by p to the m plus 1 divides clearly p to the alpha times q to the beta 1 minus 1. And this number, p to the m plus 1, does not divide this one, because we know that p to the m plus 1 times q to the beta 1 is divisible by p to the m plus 1, but we know that p to the m times q to the beta 1 does not divide, is not multiple of p to the m plus 1. And what was the motivation in this problem is to find the first change of the prime number, which was subtracted from the prime factorization of the number of n. Like at first we have assumed that p was less than q, then we have decreased p as many times as we can, and we need to look at the position there. We have to subtract q. In this case we get the number which is multiple of p to the like alpha 1, always this number, and this is alpha 1 must be greater than the previous p power, like m, otherwise we get the contradiction. So we get that if we choose two change points, like alpha 1, p to the alpha 1 times q to the beta 1 minus 1, then this point will break the statement that it will not divide the sum of the two consecutive numbers, two consecutive divisors of 10. So this was all I want to discuss for today. If you want to discuss some or consider some problem, please write in comments, and don't forget to like and subscribe my videos.